Hey there, we're going to go over some introduction to energy notes. And so in these notes, we're going to kind of characterize what is energy, look at the definition, and then we're going to look at some different forms of energy as well and see how to do those calculations. And so energy, you've probably been learning about this since grade school, and we know that energy, simply stated, is the ability to do work. So if we looked at the definition of energy, it's just the ability to do work. And that word there, work, we're going to go into that a little bit more to see what that actually means. But energy, it comes in different forms, and then all of those different forms measure the ability of an object or system to do work on another object or system. And you've probably also heard from since grade school that energy, it can't be created or destroyed, right? So it cannot be created or destroyed. And like I said, you probably learned that in middle school or grade school. But we're going to go a little bit further with that and talk about how, although it can't be created or destroyed, it can transform. And that word transform there, in other words, it can change from one form to another. Okay, so for example, I can transform from gravitational potential energy to kinetic energy. Okay, so it's not destroyed, right? But system can lose energy, or the energy can change from one form to another um, whenever we're looking at energy. The unit for energy is joules. Okay, so J-U-L-E, and we just use a capital J there. And you should be a little familiar with this because we started calculating the kinetic energy of a system in our momentum unit. Okay, so you have a little bit of experience with energy and using that calculation and the unit for energy. But again, the unit is just a joule, a capital J. Now, let's kind of look at that word that we underlined there, and that is work, and kind of see what that mean is, what the meaning of work is. So, kind of simply put, work is the exertion of a force that causes movement. Okay, so exertion of force that causes movement. Now, the important thing here in this definition is it causes something to move. Okay, so if an object is at rest, it's not moving, so there's no work being done. So if I look, let's say we have a book and it's sitting on a table. Okay, we already have some experience with drawing free body diagrams and identifying the forces. And if it's just sitting there, we know we have Fg that's going down, and we know it has a normal force going up, and those are balanced because it's at rest. So although there is a force, it's not moving. Okay, so the work in this here would be zero. Okay, there's no work being done. But let's say I go in and I apply a force to the right, and let's say that there is no friction, so now I have this applied force, and now this object is going to start moving to the right, and so this force here that I apply, now it's causing work, okay, because now I'm applying a force in the direction that it's moving. And so our equation that we get for this, for work, it's going to be this parallel force times the distance. Okay, distance needs to be in meters, and then your force is in newtons. And so what you get is newtons times meters, which is the same thing as a joule. Okay, so 1 joule is equal to 1 newton times meters. And we're going to make some more of a connection a little later with this work and how it's related to energy. So let's go ahead and start going through some of these different forms of energy that you're going to kind of be responsible for in calculating. The first one is kinetic energy. And you actually already have some experience with this kinetic energy because we started calculating the kinetic energy of a system in our momentum unit. And that's how we are able to go in and classify the different type of collision, if it's elastic or inelastic, based on if the system lost energy. And if you remember, your equation for kinetic energy was that K, capital K, equals 1/2 mv squared. And so you already have some experience using this calculation, but just to remind you, as far as a review, with kinetic energy, that is scalar, so it doesn't depend on direction because we are squaring our velocity. So if you have a negative velocity, it's going to square and the direction doesn't matter. Okay, so remember it's just the velocity there that is squared. So let's look at an example real quick to review that equation and how to calculate it. And so let's say that we want to find the kinetic energy of this three object system here. So to find the kinetic energy of this system, all we have to do is go in and calculate the kinetic energy of each object and then add them up. So let's say that this is object 1, here's object 2, and here's object 3. So the kinetic energy of your system is going to equal the kinetic energy of object 1 plus object 2 and 3. And my equation for kinetic energy is equal to 1/2 mv squared. So now we'll just go in and do that for all three objects. So for object 1, you got 1/2. You got the mass is 4 kilograms. And the velocity is -10 meters per second. That's going to be squared. Plus object 2, 1/2 times the mass, which is 2 kilograms. The velocity is 8 meters per second, and then that's squared. And then object 3, 1/2. Your mass is 6 kilograms. Your velocity is 10 meters per second squared. And so if we go in here, we square our -10 there, that becomes positive 100. Half of 4 is 2, so that gives me 200 joules, plus 8 squared, that's 64. Half of 2 is 1, so 64 joules, plus 10 squared is 100, and then half of the 6 is 3, so plus 300 joules. So the kinetic energy for your system, you're just going to add everything up. 200 plus 64 plus 300, 500, and 64 joules. So this equation here should just be a review because we've used it back in that momentum unit. Now, one thing that is a little different that we hadn't talked about is with kinetic energy, if I have an object only, so in our problem, we're either going to have an object or we're going to have a system. And this is important because if it's an object only, then the only type of energy that it can have is this kinetic energy. Okay, so if it's an object, it can only have this kinetic energy. But if it's a system, then it can have kinetic energy and it can also have potential energy. So object only, then it's just kinetic energy. If it's a system, then it can have kinetic energy and potential energy. Now we're going to look at a couple different types of this potential energy and some of the calculations involved with it. The first one is gravitational potential energy. So this is that second form that we're going to look at. And it is gravitational potential energy. And that word potential energy, it's really just stored energy. So kinetic energy deals with an object in motion, whereas potential energy is kind of stored energy. And the first one is this gravitational potential energy, and it's really due to an object's position. Okay. Now remember, you have to be part of a system. So in order to have this gravitational potential energy, I would have to have, say, a object Earth system. Okay, Earth would need to be part of my system because now I have this gravitational potential energy involved. And what's important to make note too is it's all about your frame of reference. Typically, if you're outside, let's say a student is working a problem dealing with something outside, then in that case, then the ground is your zero. Okay, so for instance, let's say I'm dropping an apple or a ball from some stands. Well, then my ground level would be my zero, and then my height would be the height from the ground. And if I'm working inside, say inside a classroom, then generally the floor in the room is zero. So in other words, I'm not worried about how far um, the floor in the room is to the ground level outside. Okay, so if I'm working in the classroom, just my floor is zero. Let's say I'm working on a lab table. If that's the case, then the table itself can be my zero. So I don't have to measure how far from from the lab table to the ground, and then how far off the lab table I am. I can just call the lab table my zero. So it's all about your frame of reference as far as where your height is coming from and what you're working with. And my equation, so the new equation here for gravitational potential is U subscript G. So the U stands for your potential, the subscript G, that's gravitational. So it's gravitational potential energy is equal to the mass of the object times G times H. So this is your mass. This is going to be measured in kilograms. G, remember, is always equal to 10 meters per second squared. And the H here is your height, and that's going to be in meters. So let's look at an example using this here. So this problem says Rudolph is patiently waiting on top of the roof for Santa to deliver presents to two children, and he's in his fittest shape of the year, and it has a mass of 160 kilograms. The rooftop is 6 meters. Calculate Rudolph's potential energy. So we're going to write down what we know. The mass is equal to 160 kilograms. G is always equal to 10 meters per second squared. And I know my height from the ground, right? We're outside, so we'll call the ground zero. So the height is 6 meters. And what we're solving for is this gravitational potential energy. So we're going to use that new equation. UG is equal to mgh, and then we'll just plug in our numbers. So we have 160 kilograms. G is always equal to 10 meters per second squared. And then your height here is 6 meters. So plug all that in, and you should end up with your UG is equal to 9,600 joules. Now look at the units here. We took kilograms times meters per second squared times meters. So what that ended up with is kilograms times meters squared per second squared, which is equal to a joule. Okay, so 1 joule is equal to 1 kilogram times meter squared per second squared. All right, let's go ahead and look at our next form of energy. Okay, and it's going to be another potential energy, and that it's called elastic potential energy. And so elastic potential energy is dependent on the value of your spring constant, okay, in other words, how stiff the spring is, as well as the stretch of the spring. So this one that we're using here, it's all about a spring, okay, kind of like with our Hooke's law. So we're looking at the potential energy, the elastic potential energy, and the ideal spring, kind of like whenever we're working Hooke's law. So this one here, our new equation, is U subscript S, so potential energy of a spring, is equal to 1/2 K. Now this is a lowercase k, that's your spring constant, times the stretch squared. So this one is your spring constant, just like it was in Hooke's law. And this is the stretch of your spring. This needs to be in meters. So the spring has to be part of your system. So for example, in a problem, if I said the spring object Earth system, then I could include both gravitational potential energy as well as the spring potential energy. So make sure whenever you're working a problem that the spring is part of your system. If it is, then there's some elastic potential energy there, and you can calculate that. So let's look at an example using this new equation. So it says we have a spring, has a spring constant of 50 newtons per meter, and is stretched 0.2 meters. How much elastic potential energy does the spring have? So we write down everything that we know. We know that the spring constant is equal to 50 newtons per meter. And then we know that it is stretched 0.2 meters. And we're looking for this spring potential energy. So our new equation is equal to 1/2 kx squared. And now we can just plug in our values. 1/2, 50 newtons per meter, times the stretch, which is 0.2 meters. And then that's going to be squared. So it's just the 0.2 that's squared here. Then you'll multiply it by 1/2 of 50, which is 25. And you should end up with, I believe, 1 joule. So now let's look at an example where we kind of tie a lot of these different forms of energy together. So this one says we have a system that includes a block, spring, and earth. So this is important to identify. Is it a system or is it just an object? Sometimes you'll see more than one object, but it's not only talking about one object, not a system, and you can't include the potential energy. Okay, so always make sure and identify what's involved, what's part of your system. Is it a system? And ask us to calculate the mechanical energy of the system. So that word mechanical energy, that's just your total energy. Okay, so in other words, we're looking at all of the energy within the system. So all of your kinetic plus all of your potential. Gravitational potential, elastic potential, you just add it all up. So my total mechanical energy, we'll use a E here for that. It's going to be all the kinetic, all the gravitational, and all the spring potential or elastic potential. And so looking at this problem here, it says that the block is not moving. So that means that your velocity is equal to 0. So that means that your kinetic energy is equal to 0. So there's not going to be any kinetic energy because the block is not moving. But there is some gravitational and some spring potential energy. So we can go ahead and calculate that. So for your total energy, it's going to equal your gravitational potential, which is mgh, plus your spring potential, which is 1/2 kx squared. So the total energy here would be 1/2 times the spring constant, which is 500, times the stretch of the spring, which is 0.1, and that's squared, plus you have the mass of your block, which is 7 kilograms. G is always 10. And then the height is 1.4 meters. So your total energy here, I square the 0.1 and then multiply by 500 and then by 1/2. So you get 2.5 joules, plus you take 7 times 10 times 1.4, that gives you 98 joules. So the total mechanical energy here of this system is just 100.5 joules. Okay, so when you're asked to find the total mechanical energy, you're just finding all of the kinetic and potential energy of that system. Be careful, if they ask you to find the mechanical energy of an object, it's just going to be the kinetic energy because an object cannot have potential energy. But there's some different forms of energy that we're going to be calculating in some examples, and then we're going to do a little bit more in class with some of these different forms of energy.